Risk is the possibility of some event, and from epidemiological perspective, it is the proportion of people in a population who are initially free of any outcome, for example any disease, later develop the outcome like any disease or illness within a specified study time period. There are two types of risk measures in epidemiology. One is absolute risk. This is when an individual, product, or idea is not compared to any other unit and is devoid of any other standards or criteria. Absolute risk examples are attributable risks, attributable fraction, population attributable risk, and population attributable fraction. Second measure is relative risk. Relative risk has a basis where one group is compared against another group. Usually, exposed group is compared to unexposed group. Relative risk examples are risk ratios, rate ratio, and odds ratio. As the incidence of any outcome like death or any disease is known among the exposed and the unexposed group, all three measures of relative risk, that includes risk ratio, rate ratio, and the disease odds ratio, can be calculated from cohort studies. Risk ratios and rate ratios can also be derived from randomized controlled trials. However, in case-control studies, the participants are selected based on the disease status, classified as either cases with a specific disease or controls without the specific disease, and not on the basis of their exposure status, and therefore the incidence in exposed or unexposed cannot be measured. It is, however, possible to compute the odds of exposure among the cases and the controls, the odds ratio of exposure. How to interpret the value of relative risk. Relative risk one shows that the incidence of illness in the exposed and unexposed groups are similar, and thus there is no relationship between the two groups. Relative risk value of greater than 1 indicates a positive connection of an enhanced risk among those exposed. Likewise, a value of less than 1 indicates an inverse relationship or a reduced risk, showing the exposure is protective. Risk ratio is absolute risk in exposed group versus absolute risk in unexposed group. The numerator for absolute risk is the outcome divided by the total number in that particular group. Risk ratio can identify if the exposure is damaging. Like in this example, people who received new drug A had twice the risk of bleeding than those who did not receive the new drug A. Sometimes the exposure can also be protective. A trial done to compare how often vaccinated and unvaccinated subjects become unwell during flu season with influenza. If 200 or 1,000 participants in the vaccinated group become infected, then the risk or probability of disease in the vaccinated is 0.2 or 20%. If 800 or 1,000 subjects in the unvaccinated group become infected, then the risk or probability of disease in the unvaccinated is 0.80 or 80%. The risk ratio in this example is 0.20 over 0.80 equals to 0.25. This means that there is a decreased risk among those vaccinated, that is, exposure is protective. Applicability of risk ratios. Risk ratios are appropriate when the time for the development of an outcome is short, but when the disease takes many years to develop, patients may be lost to follow-up or die of other diseases. When this happens, the number of study participants changes over time, making the denominator for our risk calculation unstable. Therefore, risk ratio cannot be calculated. To understand rate ratio, you need to understand the incidence rate. The numerator of incidence rate is the number of new cases in the given population, whereas the denominator is the sum of each patient's or participant's time at risk. Incidence rate in this study example is the number of people who become cases in a specific time period divided by total person time at risk during that time period. The rate ratio for this study is 0.094 per person year, or 9.4 per 100 person years, or 94 per 1000 person years. It is also feasible to calculate rates from vital statistics data where the precise measures of the person time at risk are not accessible. To achieve this, the midpoint population of the calendar period of interest is extracted and multiplied by the length of the period, that is usually years. This value serves as an approximation of the person time at risk. In this example, we see cancer deaths in population B, which is equal to 149. Mean annual cancer-related death rate was found to be 1.3 per 1,000 person years. In order to calculate rate ratio for this study, we see it was followed for 4.4 years. Among the exposed group, which are the smokers, there were 83 lung cancer deaths during 98,090 person years. Among the unexposed group, which are non-smokers, there was just one lung cancer death during 15,107 person years. Incidence death rate among smokers is 83 divided by 98,090 or 0.84 lung cancer deaths per 1,000 person years. Incidence rate among non-smokers is 1 over 15,107 or 0.07 lung cancer deaths per 1,000 person years. The result for this study shows that smokers die of lung cancer at 12 times the rate of non-smokers. This study investigates a protective effect of a high-fiber Mediterranean diet. The incidence death rate due to breast cancer was 247 per 100,000 person years in the high-fiber group and 309 deaths per 100,000 person years in the unexposed group. The rate ratio was found to be 0.80, which is less than 1. This means that a high-fiber group had an inverse association of a decreased risk in breast cancer, that is, the exposure is protective. In case control studies, the participants are selected based on their disease status, classified as either cases with a specific disease or controls without that specific disease, and not on the basis of their exposure status, and therefore the incidence in exposed or unexposed cannot be measured. It is, however, possible to compute the odds of exposure among the cases and the controls and eventually calculate the odd ratio of exposure. The odds ratio shows the odds that a disease or an outcome will occur given a specific exposure matched to the odds of the disease or an outcome happening in the absence of that exposure. Odds ratios are the most complex of all these three measures. Odds could be defined as the probability of an event occurring divided by probability of an event not occurring. In this example, we see 688 exposed cases, cell A, 650 exposed controls, cell B, 21 unexposed cases, cell C, and 59 unexposed controls, cell D. After calculating odds ratio, it was found to be 2.97. This would mean that the odds of smoking among the patients with lung cancer were 2.97 greater than the odds of smoking in patients without lung cancer. A follow-up of 10,000 people was observed over a 2-year period. Using same data, we calculated all three measures of risk, that is, risk ratio, rate ratio, as well as odds ratio. All three measures in this example gave similar estimates of relative risk, and this is common to see when the outcome is rare. Death is a rare incidence, and therefore the number of people at risk remains relatively constant throughout the study period because the cases denote a small proportion of the population. So whenever the outcome is rare, for example rare tumors or cancers, congenital anomalies, etc., we will observe a similar estimate of relative risk obtained by all three measures. However, for common conditions like infectious diseases, their relative risk may vary considerably when calculated by these three measures, as the risk may fluctuate throughout the study period. A final recap. If all three measures are greater than 1, then they suggest an unsafe exposure. Risk ratios, rate ratios, and odds ratios, if they are all equal to 1, show that a death outcome is uniformly expected among the exposed and unexposed. Risk ratios, rate ratios, and odds ratios less than 1 indicate a protective exposure. If a disease is rare, the risk ratio and the odds ratios are almost equal.